February 1st, 1943. A Boeing B-17E Flying Fortress designated All-American approaches Biskra Airfield in Algeria at 140 miles per hour, 800 feet altitude, descending at 300 feet per minute. From the ground, the aircraft looks normal. 4 engines running, landing gear extended, flaps deployed for final approach. Then it turns, and ground crews see something impossible. The entire tail section, rudder, elevators, rear fuselage, is hanging by control cables and a few strips of aluminum skin, nearly severed from the main fuselage, dangling at a 20-degree angle, moving independently of the rest of the aircraft. The structural failure should have made controlled flight impossible. The tail provides directional stability and pitch control through aerodynamic surfaces totaling 312 square feet. Without it, the B-17 should tumble uncontrollably. Yet pilot Lieutenant Kendrick Bragg maintains level flight, executes coordinated turns, and lines up for landing. Engineering manuals say this can't work. Physics textbooks say the aircraft should have broken apart at 17,000 feet when the collision occurred, but the flight engineer's logbook documents 90 minutes of controlled flight with structural integrity reduced to approximately 15% of design specifications. By the end, you'll see how aerodynamic forces, structural redundancy, and one crew's precise weight distribution turned an aircraft that should have disintegrated into one of aviation history's most documented survivability cases. But first, the mission that put All-American in the path of a BF-109, 0600 hours, February 1st, 1943. The 97th Bombardment Group receives orders to strike Axis shipping at Bizerte Harbor, Tunisia, a critical supply port feeding Rommel's Africa Corps. The target requires precision bombing from 18,000 feet through moderate flak concentrations and probable Luftwaffe fighter interception. 12 B-17F bombers will fly in tight defensive formation, a box pattern where each bomber's gunners provide overlapping fields of fire protecting the formation. All-American, serial number 4124406, occupies the vulnerable tail-end Charlie position, last aircraft in the formation, most exposed to fighter attacks from behind and below. The crew: pilot First Lieutenant Kendrick Bragg, age 24, 187 flying hours in B-17s. Co-pilot Second Lieutenant Godfrey Engel, 156 hours. Navigator Second Lieutenant Harry Nuessel. Bombardier Second Lieutenant John Humphrey, Flight Engineer Technical Sergeant Michael Zuck, Radio Operator Technical Sergeant Elton Conda, and 4 gunners, Sergeants Tyre Weaver, Samuel Sarpolis, George Eisel, and Melchor Hernandez. Total crew weight, 1,190 pounds. Aircraft weight fully loaded, 54,000 pounds, including 4,000 pounds of bombs, 1,700 gallons of fuel, and 11,275 rounds of 50 caliber ammunition for 13 defensive machine guns. The B-17F's design tolerates significant battle damage through structural redundancy. The fuselage uses semi-monocoque construction, where the aluminum skin shares structural loads with internal longerons and stringers. Combat reports document B-17s returning with hundreds of flak holes, engines shot out, hydraulics destroyed. But nobody has tested what happens when you nearly sever the tail, because no engineer thought an aircraft could survive that specific failure mode. At 0643 hours, All-American lifts off runway 09 at Tafaraoui Airfield, beginning a flight that will rewrite structural engineering assumptions. 0820 hours. 12 B-17Fs maintain tight formation at 17 to 1800 feet, cruising at 182 miles per hour toward Bizerte, 140 miles northeast. Formation spacing: 150 feet wingtip to wingtip, 200 feet nose to tail, close enough that each bomber's 1050 caliber defensive guns create overlapping fields of fire covering every approach angle. The formation geometry is precise. Lead bomber slightly higher, second element 50 feet lower and 200 feet behind, third element another 50 feet lower. All American flies in the lowest element, position purple 4, the most vulnerable spot where German fighters preferentially attack. At 0847, Bombardier Lieutenant Humphrey identifies Bizerte Harbor through his Norden bomb sight. 12 cargo ships visible at dock, 3 destroyers offshore. The formation begins its bomb run. Straight and level flight for 180 seconds at constant altitude and airspeed, required for bomb sight calculations. During these 3 minutes, the bombers cannot maneuver. They are committed to the target regardless of flak or fighters. At 0851, the first 88mm flak bursts appear at 17,500 feet, 300 yards ahead, black smoke puffs marking explosive shells that throw shrapnel in 150-foot lethal radius spheres. Pilot Bragg maintains steady heading 047 degrees magnetic, while Humphrey tracks the target. At 0853, 30 seconds before bomb release, tail gunner Sergeant Weaver reports over intercom. Fighters, 6 o'clock level, 800 yards, closing fast. Count 8, looks like 109s. The Messerschmitt Bf-109G fighters, top speed 398 miles per hour, armed with one 20mm cannon and 2 13mm machine guns, dive toward the formation's rear. Standard Luftwaffe tactic: attack during bomb run when bombers can't maneuver. Humphrey calls bombs away at 0854 12. 4 1,000-pound general-purpose bombs tumble toward the harbor from 3 miles up. But All-American won't see if they hit, because at 0854:15, a Bf-109G collides with the B-17's tail section at a combined closure rate of 280 miles per hour. 854 15 hours, 17 to 800 feet. Messerschmitt F-109G6, flown by Luftwaffe pilot Oberleutnant Franz Stiegler's wingman, attacks All-American from 6 o'clock high, diving through 420 miles per hour. The German pilot misjudges closure rate, a common error when attacking from dead astern, where depth perception is worst. At 0854 15:3, the Bf-109's propeller impacts All-American's horizontal stabilizer at station 652, 48 inches forward of the tail's leading edge. The 4-blade VDM propeller, spinning at 2,700 RPM and generating 9,140 foot-pounds of torque, acts like a circular saw. It cuts through the horizontal stabilizer's aluminum structure, 0.040-inch skin over aluminum ribs spaced 12 inches apart. The propeller severs the top skin completely, destroys 6 ribs, and continues downward into the fuselage. The Bf-109's forward momentum, kinetic energy of 47,200 foot-pounds, drives the fighter's nose through All-American's fuselage structure, cutting through longerons, stringers, and skin. The collision lasts 0.4 seconds. The Bf-109's left wing strikes the B-17's vertical stabilizer, tearing off 3 feet of rudder. Then the fighter's fuselage, now tumbling, smashes through All-American's rear fuselage just forward of the tail gunner's position. The impact severs 85% of the fuselage's circumference. Structural integrity maintained only by 2 longerons on the bottom side, control cables running through the tail, and strips of aluminum skin approximately 6 inches wide. The Bf-109 pilot, name unknown, fate unknown, ejects somewhere during the collision sequence or tumbles earthward in his disintegrating fighter. Tail gunner Sergeant Weaver, positioned 18 inches from the impact point, survives because the tail section separates aft of his position. But now, All-American flies with its tail hanging by cables, connected to the main fuselage by a structural joint with less load-bearing capacity than a household door hinge. 0854 16 hours. The collision throws pilot Bragg forward against his shoulder harness with 4G deceleration. The bomber loses 38 miles per hour in 0.6 seconds as the BF-109's mass impacts from behind. The control yoke jerks violently as elevator control cables snap. Bragg instinctively pushes forward. No response. The B-17's nose pitches up 15 degrees. Airspeed bleeds to 144 miles per hour, approaching stall speed of 138 mph at this weight. Then, unexpectedly, the nose drops back to level. Residual elevator control remains through partially severed cables. Bragg tests controls carefully. Ailerons respond normally. Roll control intact. Rudder responds partially. Yaw control degraded but functional. Elevator responds in 2-inch increments instead of smooth, continuous movement. Pitch control severely compromised but not lost. In the fuselage behind the cockpit, flight engineer Zuck moves aft to assess damage. Through the bomb bay, through the radio compartment, past the ball turret, into the waist gun section. Everything intact. Then he reaches the tail gunner's position and sees daylight through the fuselage where none should exist. The entire tail section, from station 652 aft for 192 inches, hangs at an angle, moving independently. The horizontal stabilizer, which should be rigidly perpendicular to the fuselage, oscillates up and down by 25 degrees with each gust of wind. The vertical stabilizer, which should be perfectly vertical, cants left and right by 15 degrees. Zook crawls carefully toward tail gunner Weaver, testing each step. The fuselage floor flexes abnormally, unsupported by normal structural connections. He reaches Weaver, confirms the gunner is uninjured, but trapped by wreckage. The intercom cable is severed, so Zook hand signals. "Can you move?" Weaver shakes his head. He's wedged in position by bent structural members. Zook returns to the cockpit and reports to Bragg. "Tail is hanging by cables. Estimate 85% structural separation." Weaver. Trapped, but alive. "Recommend crew bailout." But Bragg looks at his instruments. Altitude 17,600 feet and holding. Airspeed 156 mph and stable. Engines running normally. Fuel sufficient for 2 hours. The bomber is flying. Impossibly, but undeniably flying. And bailout over Tunisia means capture or worse. The B-17F Flying Fortress's tail section serves 3 critical aerodynamic functions. First, the horizontal stabilizer, 312 square feet of surface area, generates downward force balancing the wing's lift, maintaining pitch stability. Remove it, and the aircraft pitches uncontrollably. Second, the vertical stabilizer, 104 square feet, provides directional stability, preventing yaw oscillations. Remove it, and the aircraft fishtails wildly. Third, the elevators and rudder, movable control surfaces totaling 186 square feet, allow the pilot to command pitch and yaw. Remove them, and the aircraft becomes uncontrollable. All-American's tail section remains physically attached, but the structural failure eliminates rigid connection to the fuselage. In normal flight, the fuselage and tail act as one rigid body. Forces applied at the tail transfer through structural members to the center of gravity. But with 85% structural separation, the tail section acts as an independent body, connected only by flexible cables. Engineering analysis says this creates catastrophic aeroelastic flutter. The tail oscillates in resonance with aerodynamic forces, amplifying oscillations until structural failure. The calculated flutter frequency for a B-17 tail is 3.2 cycles per second. At All-American's current airspeed of 156 miles per hour, flutter should begin within 8 to 12 seconds and reach destructive amplitude within 45 seconds. Total structural failure, 60 seconds maximum. But it's been 180 seconds since the collision, and All-American continues flying. Why? 3 factors. First, the tail section's mass, 740 pounds, including structure, gunner, ammunition, and equipment, creates pendulum stability. The center of gravity of the hanging tail is below the pivot point, creating inherent stability like a pendulum hanging from a string. Second, the partially intact longerons on the bottom fuselage provide minimal but sufficient damping. They flex like shock absorbers, dissipating oscillation energy. Third, and most critical, the crew's weight distribution creates a forward center of gravity. With 9 men and equipment concentrated in the forward fuselage, moment arm of 18 feet forward of the design CG, the aircraft is nose-heavy. Normally, this requires down elevator to maintain level flight, but with elevator control compromised, the nose-heavy configuration actually helps. The aircraft wants to fly nose down, and partial elevator control provides just enough up-force to maintain level flight. It's an accidental equilibrium that shouldn't exist, but does. Like a pencil balanced on its point, unstable in theory, but momentarily possible in practice. 0.57 hours, 17,400 feet. Bragg makes the decision, we're flying home. But conventional flying won't work. The structural damage requires completely new operating procedures invented in real time. First, airspeed management. The damaged tail creates unpredictable drag and lift. Too fast, and aerodynamic forces might rip off the hanging section. Too slow, and the bomber stalls. Bragg establishes 152 miles per hour as optimal, 8 mph above stall speed, 30 mph below normal cruise, slow enough to reduce loads but fast enough to maintain control. Second, altitude management. Descending increases airspeed if not carefully controlled. Climbing requires power changes that create pitch moments. Bragg decides to maintain 17,000 feet until absolutely necessary to descend for landing. Third, crew positioning. Flight engineer Zook calculates that moving men forward shifts the center of gravity, improving pitch stability. He orders navigator Nuessel, bombardier Humphrey, and radio operator Conda to move into the nose section. 3 men, 510 pounds, repositioning 24 feet forward, shifts the CG by 1.8 inches, a small change that significantly affects pitch balance. Fourth, flight path. The direct route to Biskra Airfield crosses mountainous terrain requiring 19,000-foot altitude, impossible with compromised structure. Zook plots an alternate route following lower terrain, 260 miles versus 185 direct, but maintaining 17,000 feet or below. Fifth, communication. Co-pilot Engel radios formation leader, All-American sustained collision, severe tail damage, attempting return Biskra, request escort if available. 2 P-38 Lightning fighters detach from high cover and descend to escort the damaged bomber. Their presence will deter Luftwaffe fighters from attacking the vulnerable B-17. The crew settles into precision flying. Bragg's hands rest lightly on the yoke. Every control input must be smooth, gradual, no abrupt movements. Co-pilot Engel monitors airspeed within 2 mph tolerance. Engineer Zook watches structural strain through binoculars from the waist gun position, checking for progressive failure. It's flying, but it's emergency flying. One wrong input from structural collapse. 0920 hours. All-American flies southwest toward Algeria at 151 miles per hour, 16 to 4,100 feet altitude, escorted by two P-38 Lightnings flying 500 feet above and to each side. The bomber's damaged tail oscillates visibly. The horizontal stabilizer moves up and down through a 20-degree arc every 4.2 seconds. The vertical stabilizer sways left and right through 12 degrees every 3.8 seconds. These oscillations should grow exponentially. Aeroelastic flutter theory predicts doubling amplitude every 15-20 seconds until structural failure. But the oscillations remain constant. The severed longerons flex, absorbing energy. The cables stretch and contract, dampen movement. The system finds equilibrium at the edge of catastrophic failure, but doesn't cross that edge. At 0935, Gunner Eisel reports over intercom. Movement in tail section. Looks like Weaver's trying to reposition. Engineer Zook returns to the tail area. Weaver has worked himself free from the wreckage and needs to move. Forward. His weight, positioned 28 feet aft of the center of gravity, creates a 740 foot-pound tail-heavy moment. If he moves forward to the waist gun position, eliminating that moment, pitch stability improves. But moving through the damaged section risks shifting wreckage, breaking remaining structural connections, or falling through the weakened floor. Zook rigs a safety line, parachute harness webbing tied to structural members still attached to the forward fuselage. Weaver clips in and crawls forward, distributing his weight across multiple structural points, moving 18 inches at a time, testing each step. 4 minutes to traverse 15 feet. He clears the damaged area and collapses in the waist gun section, physically and mentally exhausted. The moment he moves forward of the damage zone, Bragg feels the control yoke pressure change. Slightly more nose-up force required to maintain level flight, indicating the tail-heavy moment has decreased. The aircraft is marginally more stable. At 1008 hours, the North African coastline appears ahead, the Mediterranean Sea visible through scattered clouds at 8,000 feet. The B-17 has flown for 73 minutes with catastrophic structural damage. But the hardest part remains. Landing requires descending, slowing, extending flaps, and landing gear. All maneuvers that change forces on the damaged structure in unpredictable ways. 10:15 hours, 14,200 feet. Bragg begins descent toward Biskra, 500 feet per minute, reducing power on all 4 engines simultaneously to maintain 152 mSh. Every control input is calculated. Descending requires nose-down pitch, which loads the elevator cables and longerons in compression. Too much pitch, and the longerons might buckle. They're designed for tension and bending, not compression, with 85% structural loss. Flight engineer Zook understands the physics. The tail section's weight, 740 pounds minus Gunner Weaver, who moved forward, creates a 560-pound mass hanging from cables and damaged structure. In level flight, this weight hangs vertically, supported by cables in pure tension, the strongest load configuration. But during descent, the tail section tilts backward relative to the airflow, creating drag force that loads the structure in shear, the weakest load configuration. Calculate the limit. 560 pounds vertical weight plus approximately 180 pounds shear force from drag at 152 mph equals 590 pounds total force on structure with 15% original strength. Original tail attachment strength, 28,000 pounds ultimate load. 15% of that, 4,200 pounds. Current load, 590 pounds. Safety factor, 7.1 to 1. Acceptable, but only if no gusts, no turbulence, no abrupt maneuvers. Zook moves to the radio compartment and looks aft with binoculars, watching the damaged structure during descent. The cables, originally slack, now show visible tension, stretched taut. The longerons, originally straight, now bow slightly under compression. The tail section's oscillation amplitude increases from 20 degrees to 28 degrees as descent alters airflow patterns. At 10 to 22 hours, passing through 10,000 feet, a moderate gust hits from the right. Wind speed spike from 12 mph to 24 mph, duration 2.3 seconds. The tail section lurches left, then right, oscillating through 35 degrees. Zuck watches the longerons bend further, visible deformation, but no failure. The structure holds, but it's approaching limits. At 10:28 hours, level at 4,000 feet, the bomber flies over the final ridge before Biskra Airfield. 8 miles to runway. Maximum structural stress still ahead. The landing sequence. 10:31 hours, 2,800 feet altitude. Biskra Airfield is visible ahead. 2 runways in X pattern. Longest runway, Aero 927, at 6,400 feet. Surface packed dirt. Wind from 280 degrees at 8 mph. Slight left crosswind. Bragg plans runway 27. Landings toward the west. Crosswind from the left. Standard B-17 landing procedure requires flaps at 30 degrees. Landing gear extended. Approach speed 110 mph. Touchdown at 95 mph. But none of that is possible with damaged structure. Extending flaps changes the wing's lift distribution, moving the center of pressure aft. That creates nose-down pitching moment requiring up elevator. But elevator control is compromised. Solution: land with 0 flaps, maintaining high approach speed. Landing gear extension is required. No choice. But the gear doors create drag spikes when opening. Bragg will extend gear at 1,800 feet, high enough that if structural failure occurs, the crew has altitude to bail out. At 10:33 hours, 1,900 feet altitude, 2 miles from runway. Threshold. Bragg calls gear down. Co-pilot Engel moves the gear lever. Hydraulic pumps whine. The main gear doors open. Drag increases 340 pounds. The nose drops 4 degrees. Bragg corrects with elevator, but the response is mushy, delayed. The tail section oscillates through 32 degrees as airflow changes. 10 seconds pass, an eternity. Then the gear locks down. 3 green indicator lights illuminate. Drag stabilizes. The bomber settles into final approach. Altitude 1,400 feet. Airspeed 138 mph. 43 mph faster than normal. Distance to runway 1.2 miles. Rate of descent 420 feet per minute. Bragg calls to engineer Zook. Watch the tail. If structure starts failing, call bailout immediately. Then to the crew on intercom. Everyone brace for hard landing. Normal touchdown speed is 95. We're coming in at 135. It's going to be rough. At 10:34 to 20, passing through 800 feet, the runway threshold is ahead. Bragg begins the final descent, knowing that in 40 seconds, physics will either prove that the impossible landing is possible or prove that some structural failures are simply unsurvivable. 10:34:45, 400 feet altitude, 0.3 miles from threshold. Bragg reduces power to idle on all 4 engines simultaneously. Throttle movement coordinated to prevent asymmetric thrust that would create yaw. The B-17 descends through 300 feet at 136 mph, sink rate 450 feet per minute. At 200 feet, Bragg begins flare, gentle back pressure on the yoke, raising the nose 3 degrees to reduce sink rate. The elevator responds sluggishly. He adds more back pressure. Nose rises 5 degrees. Sink rate decreases to 280 feet per minute. At 50 feet, Airspeed 132 mph. The runway rushes beneath them. At 20 feet, Bragg holds the nose attitude, waiting for the main gear to contact. At 10 feet, correction. At 8 feet, the right main gear touches first, crosswind pushing the bomber slightly right. The tire compresses, oleos compress, absorbing 18,000 pounds of impact force at 132 miles per hour. 1 second later, the left main gear contacts. Both mains are down. The bomber rolls on main gear only, tail still. Airborne for 2.4 seconds, covering 470 feet. Then the tail section, still hanging by cables, drops. The tail wheel contacts the dirt runway at 125 Samach. The impact sends shockwave through the damaged structure. The longerons flex violently. The cables jerk taut. But nothing breaks. The tail wheel stays connected. Bragg applies brakes, gentle, progressive, no locking the wheels on dirt surface. Deceleration 0.4 Gs, speed decreasing, 115 Mach, 105 ms, 95 mt. At 78 Mach, when at 1,800 feet down the runway, Bragg applies full brakes. The bomber slows rapidly, 65 Mach, 52 mt, 38 Mach, 24 mt. At 11 Mach, 3,400 feet from threshold, the bomber stops. Total landing roll, 400 feet. Bragg shuts down all 4 engines. In the silence after the props stop spinning, nobody speaks for 5 seconds. Then co-pilot Engel says what everyone thinks. That shouldn't have worked. But it did. 10:36 hours. Ground crews approach All-American and stop 50 feet away, staring. From the front, the bomber looks normal. From the side, it looks like 2 separate aircraft held together by hope. Chief Master Sergeant Roy Williams, head of 97th Bomb Group Maintenance, walks slowly around the B-17, documenting damage. The tail section from Station 652 aft, 16 feet of structure, is attached by 2 longerons, each 3 inches wide by 0.5 inches thick, now bent and deformed. 11 control cables, each 0.25-inch diameter steel wire, now stretched beyond elastic limit, and approximately 140 square inches of aluminum skin, torn and crumpled. Total structural connection, equivalent to less than 5% of original design strength. Williams measures the gap in the fuselage, 38 inches of empty space where structure should exist. He can pass his entire body through the gap without touching edges. The horizontal stabilizer's leading edge is destroyed. The BF-109's propeller cut completely through. The front spar, eliminating structural integrity. The vertical stabilizer has lost 3 feet of rudder, 35% of rudder area gone. Williams examines the cables supporting the tail. Normally rated for 1,800 pounds working load with 5.1 safety factor, these cables carried 740 pounds of tail weight, plus aerodynamic loads for 102 minutes of flight. He measures cable diameter, stretched from 0.25 inches to 0.28 inches, permanent deformation indicating loads approaching ultimate strength. Metallurgical analysis later shows the cables were within 15% of failure. Williams writes in his inspection report, "Aircraft sustained Category 5 damage, total structural loss. Should have resulted in immediate catastrophic failure and loss of aircraft. Continued flight for 90 minutes and successful landing defies engineering analysis. Recommend complete structural investigation to understand how aircraft remained controllable." The report goes to Boeing Engineering in Seattle. Engineers read it 3 times, checking if it's a mistake or joke. It's neither. It's documentation of the most extreme structural damage any B-17 survived in World War II. And it's proof that aircraft design includes safety margins even engineers don't fully understand. Boeing engineers spend 6 weeks analyzing all Americans' survival. Their conclusion: 5 factors combined in ways no single engineer predicted. First, structural redundancy. The B-17's semi-monocoque fuselage design distributes loads across multiple paths. When 85% of paths failed, the remaining 15% carried loads beyond design specifications but within ultimate material strength. Second, pendulum stability. The severed tail section's center of gravity below the pivot point created inherent stability, preventing catastrophic flutter. This wasn't designed, it was accidental geometry. Third, crew weight distribution. Moving men forward shifted the center of gravity 2.1 inches, changes pitch characteristics just enough to maintain control with compromised elevators. Fourth, precise airspeed management. Pilot Bragg's decision to fly at 152 mph was intuitive, but post-analysis shows it was within 6 mph of optimal speed, where aerodynamic loads balanced structural capacity. 5 mph. Faster and cables would have failed. 5 mph slower and loss of control. Fifth, materials performance. The 77.5 T6 aluminum alloy used in B-17 longerons has ultimate tensile strength of 83,000 psi with 11% elongation at failure. The damaged longeron stretched 8.7%, approaching failure but not exceeding it. The combination of these 5 factors, redundancy, geometry, weight distribution, airspeed, and materials, created a survivable condition that shouldn't exist. Boeing incorporates lessons into future designs. Additional structural redundancy around tail attachment points, improved understanding of damage tolerance, and acknowledgement that real-world survival sometimes exceeds engineering predictions. All-American never flies again. Damage is too extensive for economical repair. The aircraft is scrapped in March 1943, but the crew survives to fly 22 more combat missions in other aircraft. All 9 men complete their tours and return home. Pilot Lieutenant Bragg receives the Distinguished Flying Cross for Extraordinary Airmanship. In his citation, General Jimmy Doolittle writes, "Lieutenant Bragg demonstrated that superior piloting skills and crew coordination can overcome structural failures that theory says are unsurvivable." 80 years later, engineering students study All-American survival as a case study in damage tolerance, structural redundancy, and the gap between theoretical failure and actual failure. The bomber that landed with no tail attachment proves that sometimes the margin between possible and impossible is smaller than engineers calculate. And sometimes survival requires not just good engineering, but also exceptional piloting, crew coordination, and understanding that aircraft are more resilient than specifications suggest. The evidence is clear. He landed with no wings, or more accurately, no tail, and engineers eventually believed it, because the physical evidence couldn't be denied.